Johnny here with Simpson Math. In this video, I'm just going to introduce a way to calculate the volume of three-dimensional objects using a method called slicing. So the slices are going to be called cross sections. And those are just little slices with just a tiniest little bit of width or height to them. So a cross section is the intersection of a plane with a three-dimensional solid. So we should be familiar with this from a trig class, maybe when we talked about the conics. So here I have a cone in pencil, and then I'm intersecting that cone with a plane, and I'm doing it parallel to an x-axis. So I'm just kind of pretending that, this is the x-axis, and I've sliced the cone parallel to that x-axis. So it creates this circle cross section. So that area that they have, intersected, that's a circle. If the cone, though, is sliced vertically, so now I'm talking about perpendicular to the x-axis instead of parallel, perpendicular, so up and down, well, that creates that hyperbola shape that we learned about in trig. So you can, kind of a bad drawing here, but if I slice the cone vertically, it has this little bit of a curve to it, comes back up, and that creates that hyperbola shape. All right, so those are the cross sections of a cone if I'm doing parallel or perpendicular to the x-axis. And we're going to have that field today. So Cavalieri, I'm not sure how to pronounce his name, but they say if you have an object, like right here I've got this cylinder of the cylinder. If I wanted to find the volume of the regular cylinder, well, what I do is I find the area of the base. So this is a circle, so I would find the area of the circle, which is pi r squared. Yeah, pi r squared. That's the area of the base. And then I would multiply by the height of that cylinder. So pi r squared times height. All right. So Cavalieri says, well, if you take that regular shape that we have like those nice formulas for, and you make it irregular, so you can think of like the Leaning Tower of Pisa or something like this, and you were wanting to find the volume of this irregular shape, well, that formula doesn't quite apply anymore. But what we can do is we can take a look at little cross sections. So we're going to slice the cylinder. Looking at it like this, I think this would be parallel to the x-axis just because of the way I'm looking at it. And these little cross sections would be circles. They have an area, and I'm giving them just the tiniest amount of height, or like this width in here, this height. And, I've come up with about 12 partitions here, or 12 cross sections. And if I want to get more and more accurate, just like, depending on how irregular the shape is, but we're used to the idea of making those widths or those heights smaller and smaller and smaller. So if I wanted to sum up all of those cross sections, well, I would just add them all up. And that the idea of adding up areas or little volumes and making those heights and widths as small as possible, that should maybe ring a bell. That is integration, where I'm just adding up all of those cross sections. Okay, having a crisis off camera, but I will do my best to ignore it. Okay, so that's just what he says here, or what I have here. Solids with equal altitudes and identical cross-sectional areas at each height have the same volume. So if I can calculate the volume of this, no matter how messed up I make it, it's going to have that same volume. And I would just calculate the volume a little bit differently. I would calculate one little section at a time. All right. Oh yeah, so to calculate the volume, we're going to need to find the area, and then add up all those areas. So we're familiar with these ideas already. The area that we're talking about today will be like the area between two curves that we've practiced in the previous lectures. So we're finding area bounded by two curves or some sort of region. And then the idea of adding them all up, well, that is just integration. So above me I have like a volume formula. It's just the integration from a to b of this area formula, and that dx is just the little tiniest bit of width. So it's area, but if you add just a little bit of width, then we're talking about volume all of a sudden, and we're just adding up all those volumes. Bam. Okay, what else do I have here? Oh yeah. If I wanted to calculate the volume of this cone up here, just a reminder, I was talking about it, those cross sections as being parallel to the x-axis, or you could call that perpendicular to the y-axis, meaning it's going to have this stacked feel to it, where you're just stacking the coins on top of each other. This is giving the height just a little bit of depth to it. It's giving the height. So we need, the y is width. We need that area formula in terms of y. So we need that a of y, or we need x equals something. When we got our formula, we need it in terms of y. So x equals the y's. As opposed to the hyperbola situation, where we're slicing it with the x-axis, so perpendicular to the x-axis, like so. So now we're giving the horizontal axis, or that width, some emphasis, and we're stacking the object like so. Instead of vertically, we're doing it horizontally. So we're giving that width to the x, and we'll need that area formula, a of x, and we'll need that y equals x stuff. So we're rewriting it in terms of x. Still having a crisis off camera, so. All right, I've got that going on. That's all we're doing today, is we're going to be given some solid, and we're going to need to calculate the volume. And the way we're going to do it is we're going to come up with some area formula for the particular problem we're interested in, and then we're going to slice it up, and we're going to figure that area out, and then we're going to integrate this thing. All right. Now, today's challenge is going to be coming up with the area formula and making it fit our scenario. Sometimes we may know the radius. Sometimes we may know the diameter. Sometimes we may know the height or the base of a triangle. So we're going to keep it simple for this first introductory lecture for calculating volume by slicing. So we're going to keep it simple. We're going to have squares where maybe you know the side, then of course the area is the side squared. If you have a rectangle and you're given the side, then you would need the height. Side times h will give us the area of the rectangle. The circle, if s is the diameter, well, we know the area is pi r squared, so we just take that diameter, cut it in half. Pi r squared, area for a circle. A semicircle, that's just half of it, so you half it. It's just that top half of the circle. Triangle, half the base times the height. So if you're given some side length like s, you would need to know at least the height to continue on. If you know the side of an isosceles right triangle, well, that's just half of a square, or it's half of s squared. Okay, so keeping it simple with the types of cross sections you'll be dealing with in the homework. Then the next hard part is figuring out, do I know S? Do I know R? Am I given both S and H? So that's another challenge for today. All right. Just have the volume formula there. Now let's see if I can come up with the volume formula for something that we know. So back in 7th grade, when we first learned how to use formulas and plug and chug stuff, one volume formula we know is the volume of a sphere. So let's see if I can show where that formula comes from. Let's show that the volume of a sphere of radius r is 4/3 pi r cubed. Kind of remember that one? If you don't have it memorized, that's okay, because I'm going to show you how to derive the dang thing. Okay, so I've got some sphere with radius r. I'm going to use my trick from trig, and I'm going to take a sphere, and I'm going to put it in standard position. I'm going to position it in such a way that the center of the sphere is the origin of the Cartesian plane, the xy axis. Okay, there's my x and y axis. Now I am drawing a three-dimensional object. I've never been really good at that, so bear with me. But I'm going to, let's see if I can grab a compass. Do I have a circle here? That's too big. Let me grab my compass. And the radius of this circle or sphere is r. Maybe the radius is 1 and it's the unit circle. Maybe the radius is 500. I don't know. I don't care. It's going to be some general r. R is just some number. It's not a variable. R is the radius of the circle, a number. Okay. That means that if I were to try and label this circle, well, the farthest it goes out on the x-axis would be positive r. The furthest it goes out on the negative axis is negative r. Up top, it goes up to r. Down below, it goes to negative r on the y values. Let's see, a trick to make it look three-dimensional is to add in a circle, something like this. I'll do like a dotted line on the other side so you can kind of see. Maybe that helps visualize the sphere. Instead of a circle, it is a three-dimensional object. And what I would like to do is find the volume of this object. Okay. Well, they don't give me much information. Like, I only know that the radius is r. But I'm going to use this slicing method. So I'm going to go through and I'm going to slice up this sphere. So if I take a plane, two-dimensional plane, and I start to slice this thing up. Let's go vertically. What would those cross sections look like? If I take a plane, like a sword, and I just slice this thing vertically, what would that partition look like? Well, let's do one here. I think I see a circle. If I slice a sphere in two, the ends of that, where I slice it in two, they'd be nice circle shapes. Okay, so I've got circle cross sections, and I'm divvying it up like so. every circle will have a different size. Like right in the middle, I have this really big circle, as opposed to down here, I have a smaller circle. If I were to put one, if I slice it here, see up there, like so. I've got all these varying sizes of circles, but what I'm gonna do is I'm going to add up all the area of all the infinitesimally small areas that I can, or volumes that I can. Okay, so I claim I need to find, okay, need to find the area of the cross section. Now, because I am doing this perpendicular to the x-axis, that is me giving width to those cross sections. So we are integrating, or we're talking about dx. We're giving that x just a little bit of heft to it. Now we're going to make that as small as possible, but we're going to give it some heft. All right, now that means I need this to be a of x. The area of the cross section needs to be written in terms of x. So I want y equals something. Like y equals some x's. All right. Well, let's see. Well, maybe I can label y on here. I think I'll change color to help me see what's going on here. That very first partition that I made, the cross section that I drew, this smaller circle, I'm going to play around with that one. That circle where I sliced the sphere has some x value associated with it. Be like right here. Some x value. And this larger circle, of course, has its own x value. The biggest circle I can draw has an x value of 0, and I have negative x's as well. So this x is changing, but for the particular one I drew, the first one I drew, the x looks like so. The y, then, is that distance from the x-axis up to the highest point of the circle. I'll grab pink. All right, so I need to find the area of this circle, this cross section. It needs to be in terms of x. I need y equals x stuff. So I need kind of a y and I need an x. So I decided to just put them on there. There's an x and there's a y. And this is just for some general partitions. I'm not putting any values to this. It could be smaller, it could be 0, it could be negative. If x were 0, the y value would be r. If the x value was negative r, the y value would be 0. So as x changes, the y changes. Okay, cool. Is there any relationship between x and y? Oh, I see a triangle. If I just look at 2 dimensions, I see I can draw a right triangle so that I have a hypotenuse to this xy triangle. And in fact, I know the distance of that hypotenuse from the origin to any point on the circle or any point on the sphere. What is that distance? It is r, the radius. So I think I've come up with a relationship between x, y, and r just using the Pythagorean theorem. X squared plus y squared will always equal the radius squared. And that's the equation of a circle. All right. Now I would like to solve this for y. I want this in terms of x. So I'm going to solve this for y. I guess I will take the square root of both sides. Beautiful. Now, let's notice what y is. Y is the radius of the cross section. Y from the x. So from the x going up, that distance is y. If I needed the diameter of the circle, it would be y plus another y distance going down. So the diameter is 2y, but the radius of this cross section is y. I need an area formula in terms of x. I was trying to come up with just what y was equal to, but y in this game is not the area. Y is the radius of the circle. Okay, so I have the area of a circle is pi times r squared. So the area is equal to pi times the radius squared. Well, the radius is simply y. Oh, I can even go back to this. It's just y squared. Let me put in the radius I claim is just going to be y. Of any circle I draw, that circle will have a radius of y. I can either square the square root, or I can just go back to the previous step. I know what y squared is. It's r squared minus x squared. All right. So I've got the area of the cross section. Now, if I want to find the volume of this object, well, I'm just going to sum up all of these little cross sections. That is, I'm going to integrate from least to greatest. Now, how am I integrating this thing? Well, I'm integrating it with respect to x. So I need the least x value and the highest x value. So what is this least x value? What's the smallest number x can be? Negative r. The biggest number x can be is positive r. I'm integrating the area formula, and I'm doing so with respect to x. Okay, the pi is acting as just a constant. I can pull it out. Don't let the r scare you. They're just numbers, like a constant. The radius of that sphere is constant. So it's just a number. So when we integrate, we're just treating it r as a number. X is the variable we're integrating with respect to. Let's see, I need to go pull the pi out of the integration process. The integral of a number would be that number times x, so it's r squared x, minus the integral of x squared, well, that's 1/3 x cubed. And I still need to evaluate this thing from negative r to r. That's just using the fundamental theorem of calculus. I'm going to plug in the r, subtract, plug in the negative r. No, I did that wrong. I treated my r as a variable, but no, the x is a variable. This is, let me do that again. R squared times my x becomes r, minus 1/3 times my x becomes r, minus r squared times negative r, minus 1/3 times negative r cubed. I think I did that right. Okay, a lot of just simplification I can do. R cubed minus 1/3 r cubed minus, I'll do this one step at a time, That's a negative r cubed. That's going to remain negative. So then I'm adding 1/3 r cubed. Let's see if anything cancels. I have two of these, a negative minus that. Those also add together. So 2r cubed minus 2/3 r cubed. Oh, well, those are like variables, so I can add those together. Common denominator, multiply this by 3. This is 6r cubed thirds. I'm just kind of do that here. 6/3 r cubed minus 2/3 r cubed is 4/3 r cubed. Oh, and I've done it. Oh my gosh. Yeah. So I'll clean it up a little bit. We can say it's 4/3 pi r cubed. That would be the volume of a sphere. Okay, let me kind of walk through that again. Needed the volume of the sphere. I sliced it vertically, that is with respect to x. I'm giving these circles a little bit of width, just the slightest amount. And because of that, I need to come up with a area formula of this circle partition in terms of x. So I was stressing over what y is first, but maybe I should have stressed over the area of the circle first. But the area of the circle is pi r squared, and then I would say, oh yes, I need the radius of this circle. So I defined it in such a way that I have an x value and a y value and a radius, so I was able to solve for that radius. It would probably make more sense to do that first. Go straight to the cross-section that you need and talk about finding the area of that cross-section, what variable is needed. In this case, I needed the radius, which just happens to be the y. I was able to do it both ways, or the other direction, that's fine. And then once I have a formula for that area in terms of x, then I'm just integrating that formula from the least x value to the highest x value. All right, it just comes directly from the previous lectures where we're trying to find the area between two curves. So we take the high function minus the low function. It's that same idea. I'm just taking that top minus the bottom. I'm just coming up with an area formula. All right, let me do another example, one that's more similar to one you'll find in the homework. All right, so here's another example. A solid, so some object, has a base described as the region bounded by the x-axis and the parabola y equals 4 minus x squared. Okay. The cross-sections of the solid that are perpendicular to the y-axis are semicircles. So the cross-sections are this time perpendicular to the y-axis. So if this red line is my y-axis, then they're looking like this. And so we're talking about giving these some depth in their height. Not their width like last time, but their height. So, okay, I can do this. First, though, I need to know what this shape is going to look like. I'm going to first just graph this function. I'm going to find the region bounded by the x-axis and the parabola y equals 4 minus x squared. Okay, this is just a parabola that has been reflected about the x-axis and it's been shifted up 4. So you've got, okay, yeah, I got this. has a vertex at 0, 4. You go over 1, down 1, both directions, over 2, down 4 in both directions, keeping it nice and simple. Something like that, but all we're concerned with is this region bounded by that parabola and the x-axis. So this shaded region here. And that's acting as the base of some object. So this needs to come up off the paper. And I'm going to do so with semicircles. So I'm going to draw little semicircles here. Now, when I first learned to draw in 3 dimensions, I learned to take my axes and just kind of rotate them 135 degrees, I think. So I'm going to draw my x-axis a little bit differently. I'm going to take a look at this kind of at an angle, maybe. So I'm going to draw my x-axis going at a 45-degree angle, like so. The y-axis is coming down, but this is the positive y-axis that I'm drawing here. So, I just took that x and y axis. So I have my positive numbers over here. There's my 1 and my 2. There's my negative 1 and my negative 2. There's my 1, 2, 3, 4. Taking my x and y axis, and I've just rotated it so it looks like so. There are other ways to do this. This was just how I was taught, so this is how I do it. All right, and I'm going to draw that same shape. I'm going to have my vertex. I go over 1, down 1, over 1, down 1, over 2, down 4, over 2, down 4. And I've got this shape going on. I think I'll just draw the region this time, not the parabola. All right, now I do this because it's, I think, easier to see the picture coming up off the page. So I'm going to draw cross sections in such a way that they are perpendicular to the y-axis. Well, my y-axis is sitting here, and if I want to draw a perpendicular line, then it better look something like this. And then what's coming up off the paper into 3 dimensions, the third dimension, is a semicircle. So what I've just drawn here as my cross section, that's acting as the diameter of a semicircle. So I'm going to come up off the page the best I can. Something like that. I can draw another one on here to help me see it. I'll draw the biggest one. When my diameter is 4, the semicircle will look something like this. If I were to do a smaller one, do something like this. Even smaller, something like this. So maybe you can see the shape being formed. It's a point here, and then it's a solid, so it kind of grows up. Forming, like if I were a person standing on the other side of this thing, that'd be some giant wall, flat wall. I'll walk around this way. All right, so I've got that object. That region is acting as the base, and then these semicircles are coming up. All right, so I need to find the area of my cross section. Now, this time I am doing this with respect to the y-axis. I'm giving the y's some depth, some height to them. So I need a of y. And, well, the area of a semicircle SC for semicircle. That is 1/2 pi r squared. It's just the area of a circle, pi r squared, being cut in half. So if I want to find the area, I need to know what y is, and I would like this to be written in terms of y. I'm sorry, I need to know what the r is, and I want it in terms of y. Okay, so I said before, this entire thing from -2 to 2, my diameter here is 4. Well, it's nice that I have those values, but if I come in here, well, what's my diameter? Well, it's whatever this value is plus whatever that value is. Maybe I know that value. I'll come over to this picture. This is the diameter. I just want the radius. What's the distance from the center position to my object, the end of the object? What is that distance? It's whatever x is. Here, where I know the radius is 2, it's that x value 2. As soon as I start to come in, I don't know that value anymore, but it's just going to be whatever the x value is. So I claim x is my radius. If I needed the diameter, 2x would be the diameter. It'd be that x value plus this negative x value, but you're talking about distance. So that x plus that x gives you the diameter. Okay, so x is my radius, and that's an easy one. X equals y, so I can just plug in x for my r. That is the area of the cross section, and the cross section are these semicircles. They don't all have a diameter of 4. Some of them have, or most of them have a diameter smaller than that. But I'm going to take up all those areas, and I'm going to give them just a little bit of height to them. I'm going to come over here and say, let's give this just a little bit, just a little dy. Let's give that just a little bit more, a little dy. And I'm going to integrate this thing. I'm integrating my area formula, which is pi halves x squared dx. Oh, I'm sorry. I just went through the whole process of saying I needed a y. So I'm not ready for integrate yet. I need this in terms of y. I'll send that over here. Terms of y. So I'm not quite ready yet. Right now the radius is written as an x. So what is that as a y? Okay, well, I know how x and y are related here. I have the this relationship here. Y is equal to 4 minus x squared. That's that x right there. If I want to know the y, well, I just take this equation and I solve for y. So I'm taking the original parabola, and I'm going to solve for x. I think I will add the x squared over and subtract the y over. And if I wanted to find x, I could take the square root. Now notice though, I don't necessarily care about x. What I really need is that x squared. So x squared is just 4 minus y. So as I set up my integration, because I'm doing it with respect to y, I need it in terms of y. I almost made a mistake there. So let's integrate in terms of y. Pi halves times, it's x squared, but x squared is 4 minus y. dy. Now I'm doing this over an interval. What's the least y value and the highest y value? Well, 0 to 4. Okay, at this point, the new stuff is over. This is just old stuff now. So let me walk through this problem one more time before I get a final answer. All right, I had this region. Cross sections are perpendicular to the y-axis, or you can call that parallel to the x-axis, but it's perpendicular to the y. So it's different from my previous example. And I'm going to be integrating with respect to y. So when I get my area formula, I want it in terms of y. Okay. The area of the cross sections we're talking about are semicircles, 1/2 pi r squared. The radius is clearly this x value. That's just almost obvious. But that's not good enough, because I need this in terms of y. So I just take this x value and I rewrite it in terms of y. And the way x and y are related on this parabola is like so. So I simply solve for x squared, replace it, now I integrate. I'm going to kick out the pi halves constant, deal with that later. Ready to integrate this thing. 4y minus 1/2 y squared. I still need to integrate this from 0 to 4. The 0 will be very nice. It's going to eliminate both of those things. So really I have pi halves times 4 times 4 minus 1/2 times 4 squared minus a whole bunch of zeros. 16 halved is 8. This is 16 minus 8. So I'm getting 8 pi halves. Oh, that's just 4 pi. That's kind of a nice number, actually. 4 pi. All right. So in the homework, you're going to have some region bounded by two curves, and then you're going to have to come up with, I'll tell you the cross sections, come up with an area formula for those cross sections. How do they relate to the specific problem? It'll depend on if you're doing this with respect to x or respect to y. That'll be explained in the problem. And then you just integrate. Nice and easy. All right. Yeah. Check my notes. Look for more examples. Do the homework. Let me know if you have any questions.